All right, so we have a kind of a common theme here is that we're doing review. So if we're talking about work and work done by a constant force, we're actually going to take a little bit of a departure from this astronomical scale stuff, come back down to Earth a little bit, literally, and talk about work is equal to force times, well actually I should say the magnitude of the force, put a little vector hat over top of that, times the magnitude of the displacement times cosine theta. And of course, in grade 11, less people recognize this. In grade 12, a few more people recognize this. Does anybody recognize what kind of vector product this is? I heard it, dot product. Yep, so if you're somebody who's kind of reached ahead on this one, you know what a dot product is. If you don't, then you don't. Cross product, dot product, there's two different ways to multiply vectors that we talk about in senior math, and if you haven't gotten to it yet, you will this year. It'll be great. Anyway, the nice thing about a dot product is, well, this is the formula, vector 1 times vector 2 times cosine of the angle between them. The nice part about it is that the product is a scalar, whereas a cross product, which you'll also talk about, an example of a cross product is a torque, the answer, or the product is a vector. Torque is a vector as it turns out. Okay, so you'll get to that later on. Anyway, if I expand this out, if I was lifting an object up, I would talk about the force that I would have to apply in order to lift it up as the magnitude of mass times acceleration due to gravity, and the displacement would be the height to which I lift it up if I define the original height as height 0 times cosine of theta. Now the cosine of theta, let's think about what this means. If I've got an object, and let's just give ourselves like another little illustration here. So this is our free body diagram for this scenario. I'm taking an object and I'm putting it on top of, I don't know, like a shelf. So we're starting from position 1, we're getting up to position 2, where from here to here, this is my displacement in the y direction, my height vector if you like. So let's just say that it's a nice low shelf, 1.00 meters. I think our counters in the lab benches in the classroom are 92 centimeters or something like that. So a little higher than a lab bench. The mass is a nice round 10.0 kilogram mass. Again, keeping the numbers round. We'll make gravity by 9.81 meters per second squared. We can't have everything be round. And we make the statement that we're going to move it at a constant velocity. Constant velocity lift. And if that's the case, we would make the statement that therefore the F applied, or at least the magnitude of the F applied, as seen in this diagram, would be equal to the magnitude of the FG. Constant velocity means that the free body diagram is going to be balanced. So that's where we're getting this MAG from. Another thing is, if I sub in my values, if I have mass times, let's throw in these values, 10 kilograms, 9.81, notice it's absolute value, so I'm going to put in 9.81 meters per second squared, no plus or minus, times the height, 1.00 meters. This cosine of theta business, if my applied force is up and my displacement is also up, what's the relative angle between those two vectors? I mean, look, here's my applied force up, my delta D is up. Notice I didn't put my delta D on the free body diagram. What's the relative angle? I heard it. Theta, yeah, theta 0. 0 degrees. And people give a name to that when the displacement vector and the force vector, if you like, are in the same direction. We say that they're collinear. And it turns out that we have another name. If we apply a force this way, let's just say, on a hockey puck, while it actually slides across the ice this way. So if this was force due to kinetic friction and this was the displacement, what's the angle between those two forces? Different scenario, but if this one's 0 degrees, what's the angle between those two, not those two forces, those two vectors? Not 90, 180, yeah. So I'll put like a little thought bubble around this one. This one, theta equals 180 degrees, and people use words like antilinear. Okay? They're in opposition to each other. It's a force opposing motion, if you like. And we know that about hockey pucks. The friction's going to slow things down, right? Let's keep on going forward. but we're going to slow things down. And I know the normal force and the gravitational force are missing from that diagram. All right, so we come back over to here, and so that means that I got a cosine of 0 degrees. While I'm on this, I'm going to hit the unit curve for a second. I talked about the fact that if I have a theta axis, and I have a, I don't know what even to call this, let's just call it the y-axis. But if I have a theta axis, I know that the cosine curve has this shape for its function. And I want to think critical points. So I've got, looks like a handful, I'm just going to say 3 critical points. So at the 0 degree mark, at the 90 degree mark, and at the 180 degree mark. For that unit curve, what's the critical value point for when theta is equal to 0? 1, yeah. I mean, that's why it's the unit curve. So 1. What about when theta is equal to 180? Also 1. What about when theta is equal to 90? Did I mess this up? What did I mess up? Some people nodded their heads. What did I mess up? Come on, you guys know this one. Oh, man. Thank goodness Alex is here. Avery was just going to accept it. This is 180. Isn't this 180 degrees? But Alex steps in and says, no, honey, 360 degrees, right? The full circle. So let's try that again. At 180 degrees, what's the value of cosine theta? -1. What's the value of cosine 360? 1. Okay, so we got our critical points. We should be able to sketch out a curve like this really easily. If you're somebody who's really into the cast rule, then you can talk about why things are positive or negative as we go across the different cosine values. But I'm not going to talk about the cast rule right now, but know that that's also a thing that we could have in the back of our minds. Do you guys remember the cast rule? Yeah? Okay. So between 0 and 90, cosine is positive. Between 270 and 360, cosine is also positive. Cast rule goes like this. You guys remember, where does the C go? Top right, top left, bottom right, bottom left. Where does the C go? Yeah? Bottom right. Bottom right. Where does the S go? Top left. Where does the T go? Bottom left. And A is for all. All right? So we talk about which quadrants the theta values would yield a positive result for the cast rule for the different trig ratios. Okay? So that's something that should be in our background knowledge. If it's not in your background knowledge, or if you're like, what cast rule? Then maybe we want to talk later, okay? But that's math background. So let's go back over to what we're doing here. Cosine of 0, though, in any case, is equal to 1. So that's just going to disappear in a mathematical puff. And as we do the math, 10 times 9.8 times 1, oh, sweet. That really just ends up being 10 times 9.81, right? So 98.1. 98.1, I got to think about what the units are. The units really are, as I look at these composite units, kilogram meters squared per second squared, but nobody leaves it as that. We've talked before about the fact that there are some units, like the Newton, that are composite units or derived units that are buried in a dead person's name. Who's the dead person in this time? At this time? Yeah. Joule. Joule is the dead man. $98.1. Somebody Google it. What's Joule's first name? What's Joule's first name? So it's not John Jacob Jingleheimer Joule. I feel like it's Ernest. All right. His name is Mr. All right. So we got 98.1 joules. And yeah, joule has to always be capitalized. I think even, well, frequently in grade 11, I have to convince people you can't do a lowercase j for a joule. Anytime you have one of these buried derived units, like a joule or a Newton or a watt or a coulomb, you have to capitalize it. I capitalize your name. You should capitalize these dead people, okay? I'm trivializing it a little bit, like being silly, but I want you to remember, right? Anyway, this happens so often that we raise things to certain heights that we give it a name, gravitational potential energy, and yeah, we're doing work to put things somewhere. But gravitational potential energy is so commonly used. Gravitational potential energy. And last day we talked about the general case where there's a big G involved, universal gravitational constant. This is the special case where we're near Earth's surface, right? So the work done to lift it up to a certain height. We got pushing work. So that's lifting work. Let's think about pushing work. Again, let's give ourselves a mass. Did anybody find Joule's first name? James. Is it James? James Joule? Oh man. John Jacob Jingleheimer would have been better, but James, all right. Mass, 10.0 kilograms. And if I was going to think about sliding a mass horizontally along a surface, I actually think I'm going to add a little bit more information. I've got normal force and gravitational force. I know that gravitational force would be equal to mass times acceleration due to gravity. And I want to claim that for this one, the applied force is 15.0 newtons. Now, the fact that I've been given that the mass is 10.0 kilograms means that I can calculate the Fg. I'll just do that as a quick little aside. Fg is equal to mass times acceleration due to gravity, so that's going to be 10 times 9.81, 98.1 newtons. And I can just leave it at that. 10 kilograms times 9.81 meters per second squared, going to give you 98.1 newtons. Okay, well, that's actually the same mass that we were lifting earlier. Same values, 10 kilograms, right? So we got a force. Notice that's a newton, not a joule. And I'd like to say that I'd like to slide this thing a certain displacement. So I'm going to displace it by 12.0 meters. Somebody's going to look at this and say, well, should we have a reference frame? No, energy doesn't need a reference frame. Energy is a scalar, right? So we don't need a reference frame here. What we're most concerned about is the relative angle between the displacement vector and the forces involved. So I think to myself, okay, what should I do next? Oh, wait a minute. This is a semi-realistic block of wood. Let's say that there's some friction force, Fk. Well, if I'm going to do that, I need more information. Let's give it a mu k. Make it be 0.05. 0.05. And then just for sig figs, let's make it be 0.0500. Okay, let's just zoom in on there, in case that's not big enough for you. Okay. We actually have some questions here. We haven't even gotten to them. Look, there's I, and even down below there's I. So let's just, I don't know why that -0 is there. That snuck in. That shouldn't be there. All right, so before we get to that though, let's do a quick little figure. It seems like if we know Fg, and we know that this is on a horizontal surface, I'm just telling you it's on a horizontal surface, and there's a normal force, then we might as well just say F normal is equal to, in magnitude, to Fg, 98.1 newtons. I mean, you might have some purists out there that would say, oh, shouldn't we just say F net y equals F normal plus Fg, where F net y is 0 if you're sitting on a tabletop while you're sliding something, and then that means that if I take Fg over to the other side, F normal is equal to negative Fg. And yeah, you could absolutely do that, but can we all agree that that amounts to the same idea? Okay, so I'm going to say yes. This is definitely the more thorough way of having that conversation. All cool. But then we say, all right, well, that means that F normal has a magnitude of, well, then we already figured this out. It should be 98.1, right? Oh, no, did we? No, we didn't. 98.1 is Fg. Yeah, 98.1. I don't want to find F normal. I want to find Fk. Fk is going to be mu k times F normal. Mu k was 0.0500. F normal, remember there's no units on coefficient of kinetic friction, F normal is 98.1 newtons. And don't tell our math teacher friend, you know who I'm talking about, that I did this. But what's 98.1 times 0.05? Remember, it's going to be half of 98.1 and then move the decimal. Yeah?
4.905.
Beautiful. 4.905 newtons. Now in this case, because of our diagram, we know that it's in that direction, right? So we don't have a reference frame explicitly, but it's in that direction. It's to the left, right? So if the applied force is to the right, then the friction force is to the left. I want to come back to these I and II questions. The I says, how much work is done by the pusher? Now be careful, the pusher is doing the applied force. That's our 15.0 newtons. Notice later on it says how much work is done by friction. That's the II question. That's a different question. So let's just make sure that we've got this all framed out and we know what we're actually doing. We're not doing it all at once. We're kind of parsing this out. So how much work is done by the pusher? Well, work done by pusher, I'll just call it push, is equal to F applied times displacement times cosine theta. F applied is 15.0 newtons. Displacement is 12 meters. Cosine theta, somebody help me out. Is this collinear or antilinear? Collinear. So it's cosine of 0 degrees. And we know from the unit curve that cosine of 0 is equal to 1. So we're left with 15 times 12, and I think a lot of us can just do that in our heads, but it ends up being 180, even. 180, and then what are the units? Joules, yeah. By the way, if you can't do 15 times 12 in your head, don't be ashamed, but we really should know our times tables, right? That's important at this stage of life. I know I'm older than you are, but when I was a kid, we had to memorize our timetables up to 12 times 12 in grade 3. And there was competitions to see who could, fill in the tic-tac-toe board the fastest and all that sort of stuff. And I know that's fallen by the wayside, but if you can't do your times tables up to 12 times 12 or even beyond, by golly, you're wasting your time with a calculator. You know what I mean? Like, we should know this stuff. All right. Now, something that's kind of invisible right now is that there's a plus sign. Just sitting there invisible. And implicitly, that means that we have positive work done. Or in other words, energy was added. So there's no reference frame, but the positive sign doesn't mean direction. It means I gave this thing energy. There's a meaning to there being a positive sign, but it doesn't happen to be direction. And there's no reference frame. The next question is, the next mini question, if you like, because I'm not doing therefore statements, I'm just trying to hash out ideas here. How much work is done by friction? Now again, let's frame it properly. Work, I'll just call it work done by frick. Maybe I'll write the whole thing. I don't want to be accused of lightweight swearing. So work done by friction, or WK if you like, is equal to magnitude of FK times the magnitude. I didn't put in my magnitude lines last time around. I don't want somebody to come in and give me a hard time about that. My goodness, the online comments, they're horrendous. Cosine theta. Don't get me started on the Flat Earth Society. So I put in my FK, and my FK we already said was 4.905. Now notice that wasn't really rounded. That turned out to be an exact value. 4.905 newtons, absolute value, times displacement, still 12.0 meters. Sadly, I can't do this math in my head, but cosine of theta, what's the theta value? 180, yeah, 180 degrees. Now, according to my unit curve, cos of 180 degrees is? -1. And 4.905 is the part I can't do in my head. Cosine of 180 I could do in my head. What's 4.905 times 12? That's not a times table I learned in grade 3. 58.86. I'm not saying that we couldn't do it in our head. It's just I can't do it in a second. Maybe you can, and for which I'm proud. I'm going to leave it as joules, but there's something I'm missing. What am I missing? Negative sign. And somebody help me out. Give me the words. What does the negative sign mean? Negative work was done. That's one way of saying it. Now this is a language thing where some people get upset about it because over here we think of energy as being kind of like a paycheck. You give energy like you give somebody money. And if you pay somebody $180, that means something in today's world, right? Still means something. But if you pay somebody negative $58.86, what'd you do? You robbed them in the back alley, right? You stole money from them. And so people say negative work was done, kind of sounds like you paid them negative money. And so there are some people out there that would prefer that you say energy was robbed from the system. Or energy was removed from the system. Let's make it less about robbery, just in case that stirs up some trauma. Okay? But it's not wrong to say negative work was done. Okay? It's a matter of preference and phrasing. Now I'm going to zoom out just a little bit here. Just refocus myself. And it says find the total work done. Well, if I want to do the total work, what we're talking about is figuring out how much energy we gave to something plus how much energy we took away from something, and just say like, what's the result here, right? Now, not resultant, because that's a vector thing. What's the net effect of all the stuff that's happened? So work total equals work by pusher plus work by friction. We can sub in our values. Yes, we could have come up with a generalized equation, but we've already done the piecewise legwork. 180 joules minus 58.86 joules. It's going to be in the 120s. What do you get? Yeah, 121.414? 14 joules. That's how much energy was, removed or added to the system? Added, because it's positive. Now there's another way of thinking about this. The other way of thinking of this is sort of like I would say like a net force dynamics approach. So I just want to throw in, alternatively, if we hadn't been asked I and II, we might have done this. We might have said, hey, start off with our free body diagram. F applied, Fk. And the only reason I'm doing this is to highlight that there are alternative ways of thinking. And we could say, well, that's equal to F net. And Fk plus F applied, well, F net is equal to 15 newtons minus, as we calculated above, 15 newtons is the applied force, minus 4.905 newtons, that's the friction force, giving us 10.095 newtons as the net force acting on that box. That's from way back up at the beginning with this free body diagram up here, okay? So then we come back down here and we say, okay, well, instead of talking about it as the total work, summing up the pusher work and the friction work, why don't we just say, let's find the net work done by the net force, because that takes into account friction. So F net times delta D times cos theta. Now, F net happens to be positive, so it goes in this direction, and we would have to sort of acknowledge a reference frame in that way, I guess. But F net is 10.095 newtons. Displacement is still that 12.0 meters. Cosine of theta, remember, if the net force is to the right and the displacement is to the right, cosine of theta disappears as just a 1 because it's cosine of 0. And lo and behold, you end up getting 121.14 joules. And really the only reason I bring this up is that there's more than one way to get to the answer, right? And it depends on the logic and the thinking that you have that day. I actually like both of them. I can't say that I like one better than the other. I would say that if I was writing an exam that had a combination of dynamics problems and kinematic problems and energy problems, it's entirely possible that this might be the one that I end up landing on, because I might have already done some dynamic calculations for some reason, right? Like to figure out the acceleration of the system or something like that. So just nice to unlock that and make sure that everybody's aware of it. All right, let's take a look at this next page. Angled applied forces. Now, we've talked about angled applied forces in the context of dynamics, but now I want to talk about it in the context of energy and work. And when I look at a diagram like this, and I'll just tell you what this is an object that's being slid along a surface. I think in the dynamics unit, we talked about babies pushing bricks and things like that. Let's just make this simple. Let's just say that this is like a sled being pulled by a child by a rope. Okay, so if you like, here's the illustration. Somehow there's a rope attached to this sled. Maybe there's even a mast sitting on the sled, but this is the sled mast system, okay? And we're pulling upwards on an angle. And we say, okay, well, we're going to apply a force, 150.0 newtons. And let's just say that this kid pulling the sled is operating at an angle of 40.0 degrees above the horizontal. And say that the kid pulls the sled, let's keep the number values round again. We'll say that they pull at a displacement of 10 meters. And this time, I know we already talked about friction. This time we're going to say this is frictionless. I don't really kind of want to deal with the angle side of things right now, because I feel like if we can deal with the angle side, we can also lay the friction side back down on top of it again in homework problems. Keep in mind that this is an object that has a force due to gravity. When you're pulling up at an angle, what's going to be true about the normal force compared to the force due to gravity? Less than, right? We learned that in the dynamics unit. So I'll sort of be a little bit scale-ish about that. But this is frictionless, so there's no forces acting to the left. The question here, though, is what's the work done by this applied force on an angle? Well, the work applied, in dynamics, I'd be so tempted to find an x component and a y component to the applied force. I'd use the y component to figure out what the normal force is. I'd use the x component to do some other stuff here. But when we come to these guys, we say, okay, well, work is equal to the applied force times the displacement times the cosine of theta. That's that what we call the dot product earlier of those two vectors. 150 newtons. I know it's 150.0. 150 newtons times 10.0 meters times cosine of, what's the angle? 40. It's not 0 or 180. It's not collinear or antilinear this time. It's 40 degrees. Okay? I can't do this one in my head. I mean, the 150 times 10 I can, but not the cos 40. Can you guys tell me, what is it? I got the 1,149. What was the other thing you said? 0.6 repeated? Nice. Joules. All right, and then to 3 sig figs, I suppose. Oh, that's kind of ugly. We could say, 1150 joules, but it would really be better to say 1.15 times 10 to the power of 3 joules, just to really hammer down where the sig figs end. And people say, well, is that it? That's all you do? Well, yeah, pretty much. I do want to point out, though, people that are so committed to dynamic stuff, can you see that embedded in a dot product, what we're actually doing is, can you see that F applied times cosine theta is actually giving us the F applied x value? It's the x component of the F applied. And so when we're doing a dot product, people in math class say that we're projecting one vector onto the other vector. That's what a dot product really does. We're basically mapping its collinear component onto the other vector. And I remember I had a calculus teacher one time that said, it's like you're finding the shadow of that vector that would be projected on the surface of the other vector. You imagine what I'm saying there? Like, look, if this was the x-axis, and this was F applied. Can you see that we've just kind of, like by doing times cosine theta, we've projected that shadow onto that axis? And if the displacement's also along that axis, then we've projected the shadow onto the displacement vector. So however you think of it, but we really have dealt with the x component there. We just haven't really talked about it that way. Okay, so I'm just saying it's kind of under the hood. That's what dot products do, is they project vectors onto other vectors and multiply their collinear components along with each other, okay? I want to take a look at pushing stuff up a ramp, because that's another angled thingamajig that we've talked about. So we've got the work done by gravity, and be careful about that, by gravity, as a 10 kilogram mass slides 20 meters down a 30-degree incline. Okay, so let's label up the stuff that we know here. We've got 30 degrees. That's going to be our theta value. We've got, I guess that means that this is also 60 degrees. I don't know if that's useful. This is 90 degrees. This is a ramp, right? We know that we have, how can I do this? Maybe I don't want to do the vector going that way. Let's say that we have a force of gravity going this way. I want to actually draw the actual forces, not like FG parallel and FG perpendicular. I'm going to hold myself back from temptation, okay? But then going down the ramp, I'll make sure that it's detached from the body because it's not a force. I have my displacement, 20.0 meters. It slides down the ramp, 20 meters. And the mass, maybe I'll just also jot this off to the side. The mass is 10 kilograms. So maybe it's even the same mass from what we were talking about earlier. And now I've got these two vectors, displacement and force, and it's asking us to deal with the work done by gravity. It looks like gravity is going to be the thing dragging this thing downhill. Now, it might be that there's friction. Friction would act in this direction. And that would be equal to mu k times F normal. So we can't just totally chuck out the idea of our dynamics information because we'd need to use dynamics to figure out what the F normal is if I was going to have to figure out what the work done by friction is, right? So we're not forgetting what we've learned before. We're carrying everything forward. But if all we wanted to do is figure out what the work done by gravity is, work done by gravity would be force of gravity times displacement times cosine theta. In this case, magnitude of the force of gravity would be mass times acceleration due to gravity. I'll be a little bit less piecewise about this. Let's do it all together. Times displacement times cos theta. Mass was 10 kilograms. Magnitude of gravity, 9.81 meters per second squared. Delta D, 20 meters. Cosine of, what's the angle between the displacement and the gravity? Let's look at this. Gravity goes this way. This isn't a free body diagram. This is just me thinking about forces and their directions. Gravity goes this way. Displacement goes this way. If you like, I've just created a similar triangle to the one on the left. What's the angle between those two vectors? Got to be 60. And I guess that's why I snuck in the 60 earlier, okay? Just because it's something that we want to be able to see that there's a similar triangle being created here. 60 degrees. So cosine of 60. And if you have to draw the similar triangle to think that one out, that's cool. Do that, okay? It's all right. There's no rules against it. Anyway, if we do all of this, well, cosine of 60, isn't 60 one of those magic angles? What's cosine of 60? Anybody remember? We didn't talk about it earlier. Is it like square root of 2 or 63 or something? Yeah.
0.5.
It is 0.5, yeah. So this guy here, if you know your magic angles, this is another one, like knowing your times tables. It's nice to know these things. If this one is equal to a half, or 0.5, half times 20 is 10. 10 times 10 is 100. 100 times 9.81 is 981. 981 joules. Now, if somebody else came along and said, let's rephrase this as a slightly different question. Find the gravitational potential energy at the top as compared to the bottom. kind of bringing ourselves full circle back to the first question, okay, about lifting stuff. Only this time we're letting things down. But you'll never let me down. Find the gravitational, because you're not holding me up now. Potential energy at the top as compared to the bottom. Now, when we say as compared to the bottom, what we're implicitly saying for these gravitational potential energy problems is that we're calling the bottom height 0. And we're calling the top the initial height, okay? And this happens a lot with things like ramp problems or roller coasters or whatever, where you decide, somewhat arbitrarily, sometimes very logically, what the 0 height is. That is not the same as what we do with universal law of gravitation. Universal law of gravitation, all the measurements are made relative to the centers of massive bodies, right? These guys close to the surface of the Earth, we have to define a 0 height. So if we're doing this, we've got to figure out how high it was at the beginning. And there's nothing in the question initially that lets us know that. And so we have to be sort of inquisitive thinkers here. I'm going to draw the diagram of my ramp again. But if I know that the ramp has an incline angle of 30 degrees, and it looks like it went down by 20 meters. I don't know anything about the physical ramp, but the part of the ramp that we traversed had a slant of 20 meters. Which trig ratio you like the best? What's that? Sine, seems to me. Look at this. Isn't sine of theta, if this is the height, sine of theta is going to be equal to opposite over hypotenuse, height over 20.0 meters. So we say, all right, well, the height is equal to 20 meters, I'm sorry. 20 meters times sine 30. And speaking of special angles, if cos of 60 is a half, what's sine of 30? I'm surprised that you're learning. You guys didn't learn what sine of 30 was? Yeah. 0.25? No. It's also a half. It's also a half. Oh, by golly, what's happened to education? It's also a half. All right, 20 times 0.5 is 10. 10 meters. It's a 10-meter tall slant. I don't mean to burn people on their special angles, but we should know this stuff. It lets us go a little faster. And oftentimes textbook and tests and things like that put in special angles and things that are easy head math because they're trying to be nice to you. You know, they're trying to let you just like click, 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 click through the problem and not have to pick up the calculator and tap, tap, tap the buttons, right? So it really, not just because it's easier for tests, but yeah, maybe because it's easier for tests. Take some stress out of your life. Memorize a couple of things in this world, okay? Anyway, and I actually think that stuff like that is one of the reasons why people in the past 5 years or so have gotten much slower at test rating. Because some of those memorized knowledge bits have fallen out of our practice. We want to be able to memorize a few things, and that's really helpful. I'm saying this to you now because you'll want to know it at university, right? There is a time when this would be useful to you. It's not just like that I like to hear myself talk, although I love to hear myself talk. Just ask my wife. Anyway, e.g., mass times acceleration due to gravity at the top. So we'll call this position 1, and we can call this position 2. But at the top, e.g. 1, if you like, mass times acceleration due to gravity times height 1, 10.0 kilograms, 9.81 meters per second squared. Notice no reference frame, no negative signs. The height we just figured out was 10 meters. Oh my gosh. 9.81 times 10 times 10. 981 joules. And you think to yourself, what? This thing had 981 joules in its pocket when it was at the top of the ramp. How much did it have stolen from its pocket by the time it got to the bottom? That much, right? Rob, okay? People okay with that? Now the extra thing that I said we're not doing right now is friction. But I want you folks to know that it's fair game. You should be able to look at a problem like this, figure out what FG perpendicular is, what FG parallel is. figure out what, based on Fg perpendicular, what the normal force is. Given a coefficient of kinetic friction, figure out how much friction this object is experiencing as it slides 20 meters, and that 20 meters and that friction, are they at 60 degrees relative to each other? No. What angle are those friction and displacements relative to each other? 180, right? And so that's something that you'd want to think through, is that whole thought process. And so I'm not going to hold hands through it. I'm just going to draw your attention to it, okay? Because that's past knowledge that you should be able to recall. This isn't something that I don't think I want to spoon feed everyone, okay? So this is something that I want everybody to be able to pull out of their background knowledge.